Okay, so we'll now continue with binomial distributions. So a quick recap of the most important things that you need to know before we go for the sums. So in this video, we will be working out the sums. Okay, so before we work out the sums, a quick recap. So what are the main things when it comes to a binomial distribution? Number one, now the first important thing here is the notation. Okay, so we write this in this manner as well. X follows a binomial distribution and you write the two parameters. So we call n and p as our two parameters. What do you mean by the parameters? So over here, n represents the parameter n represents the number of fixed trials, and the parameter p represents the probability of success. The probability of success. So you recall in these binomial distributions, there are only two types of outcomes, isn't it? So there are fixed number of trials, and there are only two possible outcomes. So either the outcome is going to be a success, or either the outcome is going to be a failure. And also the probability of your success is going to be constant. Okay. And the trials are independent of each other. Any outcome will not make any effect, any impact on a future outcome. Okay. So if a random variable x has a binomial distribution with these parameters n comma p, then the probability is given by, so probability x equal r is equal to NCR into p to the power r into 1 minus p to the power n minus r. So this is what you really need to understand. Okay. So over here, NCR gives the different number of arrangements. P to the power r 1 minus p to the power n minus r gives you the probability of one path. And then you multiply by the number of arrangements. Okay. Anyway, so that's not required. That definition is not necessary. So that was what I explained in the previous part. So what we'll do here is we'll now use this equation to actually calculate probabilities in binomial distributions. Okay. Okay, so guys, let's move on to some questions now. Okay, look at the first question. The random variable x follows a binomial distribution. Look at this. So here 8 is the n value, right? N is 8. And what is 1 over 3? 1 over 3 is the probability of success. Okay, so n is 8 and 1 over 3 is the probability of success. Okay, so how do we get the probability x equals to? Shall we follow the formula? So probability x equals to, follow the formula. What do you write here? NCR. Who is n here? Guys, what's the n value here? N value is 8. 8C. What is the R value? R value is 2. And then P to the power R. What is P? Guys, what's P is the probability of success. What's the probability of success here? What is the probability of success here? 1 over 3. 1 over 3 to the power R. What's R here? In our case, R is 2. 1 over 3 to the power 2 into 1 minus P. Guys, what's 1 minus P? If P is 1 over 3, 1 minus P is 1 minus 1 over 3. Or shall I immediately write as 2 over 3? 1 minus 1 over 3 is 2 over 3. 2 over 3 to the power n minus R. Guys, what's n here? N is 8 minus R is 2. Can you see? This is all you got to do. This is how you use the equation. So 8C2, 1 over 3 to the power 2, 2 over 3 to the power 8 minus 2 is 6, isn't it? Okay, so let's type everything in the cal. 8C2, 8C2 into 1 over 3 square into 2 over 3 to the power 6. Okay, so you type the whole thing in the cal and you get the answer. So I get here, I get this figure 1792 over 6569, which is 0.273129. So it's 0.273, corrected 3 years. Okay, so can you see how the probabilities are calculated? Okay, let's go for the next part. Guys, one more thing here. So what did we actually find here? The probability x equals 2 means what? Over here we have 8 trials. So we found the probability of getting 2 successes out of 8 trials. The probability of getting 2 successes out of 8 trials is 0.273. Okay, so this is the probability that we just found now. Okay. Part B, let's move on to part B. You need to find the probability x equals 5. So what is the meaning of probability x equals 5? We have 8 trials and I want the probability of getting 5 successful trials out of 8. That's what we are going to find here. Okay, so how do we do this? NCR, that's 8C5. P to the power R. P is probability of success is 1 over 3 to the power R means power 5. 1 minus P is 2 over 3 to the power N minus R. That's power, that's 8 minus 5. So power 3. Guys, do you agree? Can I know the answer? How much is the answer? 0.06828. Yeah. 0.06828. It goes on. That means it's 0.0683. Correct 3s. Do you agree? All right, let's move on to part C. In part C, they say to get the probability that x is less than or equal to 1. What do you mean by x is less than or equal to 1? So I want to find the probability that out of 8 trials that I have one or lesser number of successes. The probability that we will have one success or less than that. So what do you mean by less than or equal 1? What are the, now you know x is a discrete random variable here, which means when you say x is less than or equal 1, can I still get all sorts of x values or do I get only very specific x values? We get specific x values. So do you remember when you get like here over here with n equal 8, what are the x values that we can get here? You know, there are 8 trials. So if there are 8 trials, x values can be what? Starts with 0, right? Do you recall? X can be 0, x can be 1, x can be 2 over here because there are 8 trials. You can go until x equals 8, right? So x equals 8 means all your trials were successful. X equals 0 means all the trials were a failure. Okay, so x less than or equal 1 means what? You can take the x value 1, right? You know, x less than or equal 1 means you can go with 1 and what? And you can take the x value 0. These are the two specific x values you can take for x less than or equal 1. You know that you don't have any other values, right? You only have the smallest possible x value you have here is 0. Isn't it? So x is less than or equal 1 means you can take 1 and you can take 0. So you get the probability of 1 and get the probability of x is 0. Are you with me? So over here, let's use the formula x equal 1. So 8c1 p to the power r. P is 1 over 3 to the power r. R is 1, right? Into 1 minus p, that's 2 over 3. 1 minus 1 over 3 is 2 over 3 to the power n minus r. So that's 8 minus 1, that's a 7. Plus x is 0 is 8c0. 1 over 3 to the power 0, so 0 successes, and 1 minus 1 over 3, that's 2 over 3 to the power 8 minus 0, that's 8. So all you got to do is what? Type the whole thing in the cal and let's get the answer and give it to 3 SF. So let's get it. So 8C1 into 1 over 3 to the power 1 into 2 over 3 to the power 7. And then plus 8C0 into 1 over 3 to the power 0 into 2 over 3 to the power 8, right? Power 8. Okay. So I just gave the whole thing in the cal. So let's get the answer. So I get this. This is okay. 0.195092, which is 0.195 correct to 3s. So this is the answer correct to 3s. Okay, so moving on to question number 2. They say the random variable t follows a binomial distribution. And this time the fixed number of trials, n is 15, and the probability of a success, the probability of a success is 2 over 3. They're asking you to find the probability t equal 5, which means what? Which means out of the 15 trials, you have to find the probability that 5 are successful. So out of 15 trials, you have to find the probability that 5 are successful, which means in other words, automatically 10 are not successful. Are you with me? Okay, let's use the equation. So probability t equal 5. So probability t equal 5, let's use the formula. So what do we get here? NCR, n is 15 now. So 15 C5 p to the power x. So p is 2 over 3, right? 2 over 3 to the power x is 5. 1 minus p. Guys, what will be 1 minus p? If p is 2 over 3, if the probability of success is 2 over 3, 1 minus p, the probability of failure will be 1 minus 2 over 3, isn't it? 1 minus 2 over 3, or you could directly write the answer as 1 over 3. So that will come to the power of n minus r. 15 minus 5. 15 minus 5 is 10. Guys, do you agree? Can I know the answer? You can directly type this in the cal. 15C5, 2 over 3 to the power 5 into 1 minus 2 over 3 to the power 10. What's the answer? What is the answer? 6.697 into 10 to the power minus 3. So if you make it to 3SF, it's going to be 6.670, right? 67. So in other words, this is 0.00667, isn't it? 0.00667. Yeah. This is correct. Let me check again. Wait, let me rewrite it again. It's 6.697095. It goes on 10 to the power minus 3. When you fix it to 3SF, I think you can see 1, 2, 3. The third figure is 9. When you add 1 from 7, it's going to be 6.70, right? Correct to 3SF, 6.70. Correct to 3SF. And then when you write it off, 0.00670. So basically 0.0067. So that's the probability. Okay, so that's the answer. Okay, next part, you have to get the probability t is equal to 10. So let's use the equation probability t equal 10. So 15, 10, 15C10, p to the power r. That's 2 over 3 to the power r is 10. 1 minus p, so 1 minus 2 over 3 is 1 over 3 to the power n minus r. 15 minus 10 is 5. So what do we get for the answer? Let's type everything in the cal. What's the answer? 0. 0.21 0.214307. It goes on, right? Yeah, so then you can give it to 3SF 0.214 to 3SF. Okay, so this is the final answer. Next one, probability. T is greater than or equal 3, less than or equal 4. Guys, what are the T values that are included here? Greater than or equal 3, less than or equal 4. So this includes the T value of 3. You know, T is discrete, right? And the T value 4. So you don't have anything more, right? There are no T values in between 3 and 4 because it's a discrete variable. So over here, the random variable T represents only the integer figures, right? So integer figures in this case, by the way, what are the integers that T can take? If there are 15 trials, what are the values that T can actually take? T can take any value between 0 to 15, all the integer values. So T can take any integer value between 0 and 15. The lowest value 0, the largest value 15, and any integer in between that, right? Because it's the number of trials, okay? The number of trials, the number of successful trials. Can be anything between 0 and 15 because you have 15 trials, okay? All right, so let's get the answer quickly. T equals 3. I'll do it over here. So 15 C3 T to the power. So 2 over 3 to the power 3. 1 minus 2 over 3 is 1 over 3 to the power 15 minus 3. That's 12, right? Plus 15 C4. 2 over 3 to the power 4 into 1 minus 2 over 3 is 1 over 3 to the power 15 minus 4. That's 11. So you need to type the whole thing in the cal. What's the answer you get? Yeah. Yeah. So we get here 1.775744501 into 10 to the power minus 3. Okay, so you need to type this in the cal. So correct to 3SF 1.78. Isn't it? Or in other words, 0.00178 correct to 3SF. This is clear? Okay, so now let's move to question number 3. Okay. A student suggests using a binomial distribution to model the following situations. Define the random variable, state any assumptions that must be made, and give possible values for n and p. So you know n represents the fixed number of trials, p represents the probability, the constant probability of success. Okay, so you're supposed to define the random variable, meaning you're supposed to say who x is. Okay. Okay, look at this. A sample of 20 balls from a large batch is checked for faults. It is estimated that 1% of all balls produced will be faulty. Okay, so your task is, okay, they are saying, what are you supposed to do here now? You're supposed to what? You're supposed to model this by using a binomial distribution. Okay, so how do you model this by using a binomial distribution? Now, in part A, first thing is to define the random variable. How do you define the random variable? X is what? What are we checking for? In this large batch, what are we checking for here? A sample of 20 balls from a large batch is checked for false. Basically, we take the ball and we check whether it is good or whether it has any fault in it. So what are we doing here? X is always X will be the number of it has, you're always counting something. This is a discrete variable, right? You'll always be counting. So what are we counting here? What are we counting here? Number of faulty balls. That's what we are counting here. Do you agree? Okay, so out of these 20 balls in this batch, you check for faults. So what you do is out of 20, you check how many have faults. That's what we do here. So X is the number of faulty balls. Okay, and then, so what do you think about the distribution? The number of faulty balls in a batch of how much? In a sample of 20. And then immediately this tells you the binomial distribution. What's the fixed number of trials? We are checking from the very beginning, we've been told that we are checking 20. And what's the probability of success? The probability of success in this case is the probability of getting a faulty ball because we are checking the faulty balls, a defective ball. So in that case, the probability of success is the probability of getting a faulty one. So what's the probability of getting a faulty one? 1%. So 0.01. Can you see? So if you define X as the number of faulty balls, then getting a faulty ball is what we consider as a success here. Okay, so it all depends, the success failure depends on the way you describe your random variable. Is this clear? So over here, what is the n value? We use n as 20 and we use the probability of success as 0.01. That's what we did over here, right? And then what about the assumptions? Did we do, are there any assumptions that this needs to obey? So in binomial, there has to be a fixed number of trials that is already given. Do we need to assume it? No. The probability of the success is 1%. That's also given. It is estimated that 1% of the balls produced will be faulty. That's also given. We don't need to assume it. So what more do we need to assume here? In order for the binomial distribution to work, do you remember another one important rule? What is it? The trials must be independent. Isn't it? The trials must be independent, which means these balls are becoming faulty independent of the other. Okay, so what's the assumption? Assume the balls are faulty independently or independent of each other. So one ball being faulty will not make any impact on the other one. So this is what you're supposed to do. They just want you to model each situation by a binomial distribution. Okay, let's go to part B. Okay, so we'll move on to part B. Some traffic lights have 3 settings. So stop, that is red, 48% of the time. Wait or get ready, that is orange, 4% of the time. And go green, which is 48% of the time. Assuming that you proceed forward only when the light is green. Okay, you proceed forward only when the light is green. Model the number of times that you have to wait or stop. So guys, this is important. What are they asking you to model? You have to model the number of times that you have to wait or stop on a journey passing through 6 sets of traffic lights. Okay, they are asking you to model the number of times you have to wait or stop. So you're passing through 6 sets of traffic lights. Okay, so what are you going to discuss? I mean, who is going to be your variable X? X is always a number. Remember, X is always going to be number. So X is going to be the number of. So what are we modeling? Number of times that you have to wait or stop. Number of times that we wait or stop. Okay, number of times that we wait or stop. Actually, through how many? Through 6 sets of traffic lights. So through 6 sets of traffic lights means this gives you the fixed number of trials, isn't it? So what's the n value here? N value is 6. Guys, what's the probability of success? The important thing here is probability here is you calculate the probability with respect to what you are modeling. What are we modeling? You are modeling the number of times that we wait or stop. So what's the probability of waiting? I think you can see waiting and stopping. Stopping probability 48%. This waiting is the orange light, isn't it? So stopping is 48%. Waiting, the orange light is 4%. The other one is the green. That is where you go forward. So stopping or waiting is the red light or the orange light, which is 48% and the 4%. What are you supposed to do? So together, it's a or. You should add the two probability. 48% plus 4% is 52%, or in other words 0.52. So then you can model this through X follows a binomial distribution with fixed number of trials is 6. Probability of success is 0.52. This is clear. And then what about the assumption? So what do you assume? Once again, the number of trials are given. The probability of success is also given. So what's the main assumption we have to go here? The main assumption that we go here is that the number of times that we stop is what? Is independent, right? The amount of times that we stop, that's independent of each other. Okay, let's go to part C. Moving on to part C, when Stephanie plays tennis with Rashmi, 1 in 8 of her serves. Can you see 1 in 8 of her serves? So that's like a probability, right? On average is an ace. Stephanie serves 30 times. So she's serving 30 times. How many aces does she serve? So basically what are we doing? X is what? The number of aces, right? The number of aces in 30 serves. X is the number of aces in 30 serves. So n is the fixed number of trials. That's going to be 30. And the probability of success is? What's the probability of serving a ace? So they say 1 in 8 of her serves. So probability is 1 over 8. Do you agree? Probability is 1 over 8. Okay. And then all you got to do here is, so let's write X follows a binomial distribution. N is 30. Probability of success is 1 over 8. And what about the assumption? So you assume serving an ace, serving aces are independent of each other. Is this clear? Okay. Okay, so next I'll move on to question number 5. Okay, they say a balloon manufacturer claims that 95% of his balloons will not burst when blown up. Okay, you have 20 of these balloons to blow up for a birthday party. What is the probability that none of them burst when blown up? Okay, so how do we do this? First thing is you have to define your variable x. How do you define x? X is the number of balloons that what? Number of balloons. Now you need to decide which way you go here. Number of balloons that burst or that do not burst. But the number of balloons that burst when blown up. So if you define x as the number of balloons that burst, so what does x follow? X follows a binomial distribution. What's the fixed number of trials? How many balloons are we using here? 20. And what's the probability of bursting up? Because what's the probability that it bursts? The balloon manufacturer claims that 95% of his balloons will not burst. So if 95% of the balloons will not burst, what percentage of the balloons will burst? It will be 5%. So remember, it's extremely important you give the probability with respect to the variable that you define. Okay, so over here, if I define x as the number of balloons that burst when blown up, then x follows a binomial distribution, n is 20, and the probability of success is 0.05. The probability of that balloon will burst. Okay, so part A, what probability are we supposed to find? What is the probability that none of them burst? So x is the number of balloons that burst. If none of them burst, what's the x value? X is equal to 0, right? If none of them burst, right? So x is 0 means none of the balloons burst. So let's now use the equation. Let's now use the equation. So what was the equation for probability capital X equals simple x? It was NCX p to the power x 1 minus p to the power n minus x, right? So let's do that. 20C0 p to the power x 1 minus p 0.95 to the power n minus x, 20 minus 0. Guys, get the answer here. 20C0 20C0 0.05 to the power 0 is a 1, right? So I'll just leave it as a 1 into 0.95 to the power 20. So I get the answer 0.358485 goes on. So 0.358 correct to 3 is it. Okay, and then we'll move on to part B. So this is the answer for part A, right? I hope everything is clear. Part B, what is the probability that exactly two balloons burst? So if exactly two balloons burst, what's the X value? Now here I have defined X is the number of balloons that burst. So if exactly two balloons burst, that means X is equal to 2. So how do you get the probability X equals to 2? So 20 C2 p to the power xp 0.05 to the power 2 into 1 minus 0.05. That's 0.95 to the power n minus x. 20 minus 2. That's 18. What's the answer? So 20 C2 into 0.05 to the power 2 into 0.95 to the power 18. So I get the answer 0.18867. Can you see? So it's 0.1886 is 0.189. Correct to 3 years. Can you see how you model the probability distribution sums? So you read the question, you make the variable, you define the probabilities, and you get the answer. Is this clear? Okay, so moving on to question 8. A dice is biased so that the probability of it landing on a 6 is 0.3. Vivek rolls the dice 15 times. State any assumptions that are required to model the number of sixes as a binomial distribution and state the distribution. So what is the main assumption we require? I think you can see here you are landing on a 6. So x should be the number of sixes, right? X is the number of sixes. And then what's the assumption? We assume that sixes occur independently. Or you can assume that the dice rolls independently. You can say that the dice rolls independently. All right, and then X follows. They're asking you to state the distribution. So state it. X follows a binomial distribution. What's the n comma p? N is the number of trials. How many trials do we have here? Vivek rolls the dice how many times? 15 times. So you have 15 trials. And what's the probability of success? The probability of success is getting a 6 because we are modeling the number of sixes. So that's 0.3. That's the part A answer. Part B, find the probability that Vivek rolls exactly 4 sixes. So you have to find the probability x equals number of sixes is 4. So x equals 4. How do you get the probability x equals 4? So NCR 15C4 p to the power x. P is 0.3 to the power x is power 4 into 1 minus p to the power n minus x. So 15 minus 4. I hope you guys follow the equation, right? What's the answer? You have to type this in the cal. 0.219 to 3SF. So I didn't go to type in the calculator. You need to type it and get this answer. You should be able to get this answer. Part C, find the probability he rolls 2 or fewer sixes. Guys, what do you mean by rolling 2 or fewer sixes? X is less than or equal to, right? 2 or fewer. So which means what are the X values that we could possibly get? X equals 2. It could be x equal 1 or it could even be x equals 0. You know that this is how the variable works. So x equals 2 probability you get by 15C2 0.3 to the power 2, 1 minus 0.3 to the power 15 minus 2. That's 13. Right? Then the next one, x equal 1, 15C1, 0.3 to the power 1, 1 minus 0.3 to the power 15 minus 1 is 14, plus 15C2, 0.3 to the power, 15C0, 0.3 to the power 0, 1 minus 0.3 to the power 15 minus 0. So it's a matter of what? Giving everything over here in the cal and then you can get the answer. What's the final answer? 0.1268, it goes on. So 0.127 to 3s. If I didn't give the calculator part, so you can type it in the cal and check your answer. Okay, so I hope this is clear with everyone. So this is the beginning of modeling data by using binomial distributions.